Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we're doing a deep dive into something that's really at the heart of all modern electronics, the extrinsic semiconductor. It's from Unit 14, Semiconductor Electronics.
And the goal is to make it super simple.
Exactly. So simple, but also completely exam safe, so you understand the physics behind it and, of course, score those maximum marks. Okay, so let's start with a question, a really basic one. We know that pure silicon, that's intrinsic silicon, is a semiconductor.
Right.
But the thing is, it's a terrible conductor.
Yeah.
Almost an insulator, really, at room temperature. Its conductivity is just, well, it's too low to be useful.
For any actual device, you mean?
For any practical device, yes. So here's the big question. How do engineers take this almost useless material and, by adding just a tiny, almost invisible pinch of something else, make it conduct electricity millions of times better?
That does sound a bit counterintuitive.
It does, doesn't it? What is this master stroke, this trick that gives us the reliable current we need for, every single transistor in our phones and computers?
Because usually, in chemistry, we're taught that purity is everything. Adding an impurity? Well, that's contamination. It should ruin the crystal, not make it better.
That's the logical assumption.
Yeah.
That it should make things worse, maybe decrease the conductivity.
So how can contaminating something be the very thing that makes it so powerful? It's a bit hard to wrap your head around at first.
Well, this is where the physics is just, it's amazing. And we have to shift our thinking. This isn't contamination. It's a very precise, very controlled engineering process called doping.
Doping, okay.
And the results are just staggering. I mean, look, our sources say that adding just 1 part per million, think about that.
1 atom for every million silicon atoms.
Yes. Just 1 foreign atom in a million can increase the semiconductor's conductivity by a factor of, get this, 360,000 times, or even more.
360,000.
Unbelievable, isn't it? This tiny, invisible amount completely transforms the material from something useless into the absolute core building block of all our digital technology. This is how we create what we call an extrinsic semiconductor. So let's define that core idea. Let's get the mental picture right. An extrinsic semiconductor is basically a pure semiconductor that we have deliberately, doped.
Modified.
Modified, exactly. To create an unequal number of free electrons and holes, we unbalance the system on purpose.
And why do we have to do that? Because the pure one is so weak.
Precisely. In pure silicon, the intrinsic carrier concentration, or $9, is only about 10 to the power of 10 per cubic centimeter. That's a very low number for devices. It gives you a very low, very unstable conductivity.
Unstable because it depends too much on temperature, I suppose.
Exactly. But the moment we dope it, we get a high, stable, and most importantly, a controllable conductivity. So let's use an analogy. The audience voting model. Imagine a town meeting. This is our intrinsic pure state. You have an exactly equal number of men, who are our electrons, and women, who are our holes.
Perfectly balanced.
Perfectly balanced. The result of any vote is very sensitive. A small change could tip it either way. Now, doping is like deliberately bringing in, say, 1,000 extra voters of just one gender.
Ah, so you're stacking the deck.
You're stacking the deck. The system is now extrinsic. It is dominated by the majority voters you added, and the outcome of the vote, the current flow, is now reliably controlled by you, by the number of dopants.
I see. So this creates 2 different outcomes.
2 different types, yes. First, you have the N type. The N is for negative. Here, the impurity atom, something like phosphorus, replaces a silicon atom. Now, phosphorus has 5 valence electrons.
But silicon only has 4.
Right, so 4 of phosphorus's electrons form bonds with the silicon neighbors, but that leaves 1 extra electron just sort of hanging around.
Okay, and the other type?
The other is P type. P for positive. Here, the impurity is something like boron. Boron is trivalent. It only has 3 valence electrons. So when it replaces silicon, it's actually 1 electron short of making all 4 bonds.
Creating a missing electron.
Or a hole.
Exactly. It creates a hole.
Here's something I'm wondering. What is the real secret here? Why is that extra electron from the dopant atom so easy to free? You said it only takes about 0.05 electron volts, which is tiny compared to the 1.1 eV needed for an electron from the silicon itself.
That is the pivotal point. That is the engineering trick that makes everything work. Think about that phosphorus atom again.
The donor atom.
Yes, the donor. It's sitting there with 4 perfect bonds to the silicon atoms around it. That 5th electron, it's very weakly bound to its own nucleus.
Why is it so weak?
Because the positive charge of its nucleus is effectively shielded or screened
Yeah.
by those 4 other electrons that are locked in the bonds.
Mhm.
So this 5th electron is just,
Oh.
it's on the outer edge, almost free already.
So the energy you need to kick it loose and make it a free conduction carrier is just a tiny 0.05 eV. And at room temperature, the available thermal energy is about 0.025 eV.
Which is more than enough to easily knock it free.
More than enough. This means practically every single dopant atom we add immediately contributes a stable free carrier. We get a massive fixed supply of charge carriers that isn't really affected by small temperature changes.
So basically, doping gives us a reliable source of current that isn't as vulnerable to temperature fluctuations, because the carriers come from the dopants, not from breaking these strong silicon bonds. That makes a lot of sense for building reliable circuits.
Precisely. Now we've got the why and the mechanism. Let's bridge this to the formal NCERT concepts, just to make sure our language is absolutely exam safe. Could you please read out the exact definition for an extrinsic semiconductor from our source, and also mention the condition for doping?
Of course. Source 1 says, when a small amount, say a few parts per million ppm, of a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor is increased manifold. Such materials are known as extrinsic semiconductors or impurity semiconductors.
Good. And the condition?
Ah, yes, the condition is critical. It says, the size of the dopant and the semiconductor atoms should be nearly the same. This is to ensure the crystal lattice is not distorted.
Excellent. The structural integrity is key. That's why it's engineering, not contamination. Now let's formally compare the two types based on the valence of the impurity. This is a big scoring point.
Okay.
Let's start with N-type semiconductors. These are doped with a pentavalent impurity. That means an element from group 15, like phosphorus, arsenic, or antimony.
With 5 valence electrons.
Correct. And because each atom donates 1 extra electron for conduction, we call them donor impurities.
They donate an electron. Makes sense.
And the result is critical. Electrons become the overwhelming majority carriers. So the electron concentration, $, becomes vastly greater than the hole concentration, none $.
Is much, much greater than $.
About it.
Now, for P-type semiconductors, these are formed by doping with a trivalent impurity, an element from group 13.
Like boron or aluminium.
Exactly. Indium, boron, aluminium. Now, these impurities accept an electron to complete their bonds, which creates a hole. So we call them acceptor impurities.
They accept an electron, creating a positive hole.
And so the outcome here is that holes become the majority carriers. So $, is much, much greater than $.
The complete opposite of N-type.
The exact opposite. But here's a fundamental point that many students miss. In both N-type and P-type, the crystal as a whole remains electrically neutral.
How so? We're adding charges.
We are adding mobile charges, yes. But the charge of these new carriers is perfectly balanced by the charge of the fixed, ionized dopant atoms left behind in the lattice. So overall neutrality is maintained.
Okay, that's a very important clarification. It is, and this leads us to the most fundamental mathematical rule for all semiconductors in thermal equilibrium, the mass action law. This is a must-know formula for exams. It simply states that the product of the electron and hole concentrations is a constant. That constant is $92. So $9 times $1 always equals $9 squared.
Always, whether it's pure or doped.
Always at thermal equilibrium. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's use a quick example to see the real power of that mass action law. This really shows the trick of doping.
Okay.
Suppose our pure silicon has an intrinsic concentration, $9, $4, $10 centicarats per cubic centimeter. That means $9 is $10 and $9 is also $10.
No, $10 is 10 to naught. That's our constant.
That's our fixed constant.
Yeah.
Now let's dope it to make it N-type. We add, say, 1016 atoms per cubic centimeter. Since they all donate an electron at room temperature, our new electron concentration, $9, jumps to about 1016.
Whoa. That's 1,000,000 times more electrons than before.
1,000,000 times. Now, what happens to the holes? The product, 9 times $, must still be 1020.
Right. So we have to calculate the new
Just divide. We take $2, which is 1020, and divide it by our new nullars, which is 1016.
And that gives 142.
Oh, wow.
See, the whole concentration drops from 1010 all the way down to a tiny 144 per cubic centimeter.
So we don't just add 1,000,000 times more electrons. We simultaneously crush the number of holes. They get reduced exponentially.
Exactly. That is the point. Doping doesn't just boost the majority, it actively suppresses the minority carrier through a huge increase in recombination. the mass action law must be obeyed. And this is why the conductivity is now completely dominated by the majority carriers, giving us that massive improvement.
I see. That makes it so much more stable and predictable. Completely. And these two engineered blocks, the N-type rich in electrons and the P-type rich in holes, are the building blocks we need. We put them together to form the PN junction. And that is the one-way valve for current that enables all of electronics. Okay, let's switch gears and talk about 2 or 3 silent killers. These are misconceptions that often cost students marks.
The common traps.
The common traps, yes. Misconception number 1, that doping is just adding a lot of impurities and that it's basically contamination that ruins the crystal.
Which we already established is wrong.
But students still write it. The correction is this. Doping is precise engineering. It's done at the parts per million level. The atom sizes must match. It enhances conductivity on purpose. It does not ruin the crystal.
So precise engineering, not contamination.
You must use those words. Now, misconception number 2, which is related to the mass action law. The wrong idea is that when you add donor atoms to make N-type material, you only increase the number of electrons, and that the number of holes just stays the same.
But we just calculated that it drops drastically.
Exactly. The correction is that you must explain the shift in equilibrium. Yes, Norcley increases dramatically, but Nordeller's the whole concentration is drastically suppressed. Why? Because with so many more electrons around, the rate of recombination with holes shoots up. This forces the whole countdown until the product entropy rebalances to equal 922.
So just saying Noro increases is only half the answer. You have to also state that the minority carrier, in Dorler's in this case, is actively suppressed.
Absolutely. If you miss the suppression part, you lose marks. You're showing you don't fully understand the equilibrium. It shows an incomplete picture. Okay, to make sure this never gets confusing under exam pressure, let's lock in a couple of memory anchors.
Good idea.
First, a simple acronym, DNP. Just remember, DNP. D is for donor, which makes N-type material, which has a negative carrier majority. A is for acceptor, which makes P-type material with a positive carrier majority.
DNP. Donor N-type, acceptor P-type. Simple enough.
And a catchy phrase for the valence. Donors give electrons, so they are pentavalent from group 15. Acceptors take electrons, so they are trivalent from group 13.
Even take. Okay, that's easy to remember.
And finally, a physical gesture to really get the mental picture. Start with both your hands held together, level. This is the intrinsic state equal carriers. Balance.
Hands together.
Now, for the extrinsic state, make one hand completely full, representing the huge number of majority carriers, and make the other hand almost empty, symbolizing the massive suppression of the minority carriers. That imbalance, that's the superpower we engineer.
Right. One handful, one almost empty. I like that visual.
It helps. Okay, let's wrap this up. I'm going to give you exactly 3 short, exam-safe summary points. The absolute essentials.
Let's have
1. Extrinsic semiconductors are made by a controlled process called doping. The goal is to get high tunable conductivity, which is far superior to the uselessly low conductivity of intrinsic material. 2. N-type semiconductors are doped with pentavalent or donor impurities like phosphorus. This makes electrons the majority carriers, so Nosers is much greater than 9. And 3. P-type semiconductors are doped with trivalent or acceptor impurities like boron. This makes holes the majority carriers, so nones is much greater than $. And in all cases, the product $, remains constant at 923.
clear, concise, and covers all the key points.
For achieving maximum marks in 12 CBSE physics, chemistry, and maths, please visit ProfSam.com.
That is ProfSam, right?
Yes, precisely. ProfSam.com. Keep learning, keep asking smart questions, and we will see you on the next deep dive.